In section 3C, we're going to talk about dealing with uncertainty. So the first thing we discuss is significant digits. How are digits significant? Okay, so non-zero digits are always significant. Some zeros are significant, but not all of them. Zeros that follow a non-zero digit and lie to the right of a decimal point are significant. So like 3.20 or 3.00 or 300 or 1,000. Those zeros are significant. If they're to the left, they wouldn't be. Zeros between non-zero digits like 4,002 or 3.06 or other significant zeros like 30.0, all those are significant. So this number would have 4 significant digits. This one has 3 and this one has 3. And then back up on the second row, that number has 3 and that number has 3 significant digits. Zeros to the left of the first non-zero digit in a decimal are not significant, which might seem kind of odd. So in 0.006, it has 1 significant digit. And in 0.00052, it has 2 significant digits. And we'll see that the reason for that is often because you could use smaller units and write it without the zeros. Zeros to the right of the last non-zero digit, but before the decimal point, like in 40,000 or 210, are not significant unless otherwise stated. So 40,000 only has 1 significant digit, and 210 only has 2 significant digits. So for this example, we're going to state the number of significant digits and the implied meaning for each number. So the first one, a time of 11.90 seconds, or 11 and 90 hundredths of a second. This has, because the zero after is concluded, 4 significant digits. And it implies a measurement to the nearest one hundredth of a second. A length of, I don't even know what that, let's see, tens, hundreds, thousands, 10,000s, one hundred thousands, millions. So 67 millionth of a meter. This has 2 significant digits. I'm going to abbreviate SIGDIG, okay? And it implies a measurement to the nearest tens, hundreds, thousands, 10,000s, 100,000, 1 millionth of a meter. Now, the reason that this has only got 2 significant digits is because note that this could be written as 67 micrometers or micrometers, depending on how it's said. Then that shows that it could be just 2 significant digits. What about a weight of 10/30 of a gram? I have to stop and think about it. That is, again, 2 significant digits, because the ones before the 3 don't count, but after do. Again, this could be written as it's equivalent to 3.0 milligrams. The final digit is significant because there's no reason, or the final 0 is significant because there's no reason to include it unless it was measured. So if it's measured, it's significant. A population reported as 240,000. Again, zeros to the right aren't significant, so this is 2 significant digits. And it implies a measurement to the nearest 10,000 people. And a population reported as 2.40 times 10 to the 5th has 3 significant digits. And it implies a measurement to the nearest 1,000 people. And you can tell that because it'd be changing from scientific notation, it'd be 1, 2, 3, 4, 5, 240,000. Example 2 says, for each of the following operations, give your answer with the specified numbers of significant digits. So we want to multiply 7.7 millimeters times, or let's say this correctly, 7 7/10 millimeters times 9 92/100 millimeters. Okay, so you just multiply. 7.7 times 9.92 is 76.384. Millimeters times millimeters is millimeters squared. But it says 2 significant digits, so we just need to stop at the 38. 76.38 millimeters squared. And B, multiply 240,000 by 72,106 with 4 significant digits. So that would be, if you put that in your calculator, you get it back in scientific notation, 1.730544 times 10 to the 10th. With 4 significant digits, we round to there. So 1.73, and we need to round the 0 up to 1 because the next number is 5, times 10 to the 10. Types of measurement error. There could be random errors because of random and inherently unpredictable events in the measurement process. Okay. Systematic errors occur when there's a problem in the measurement system that affects all measurements in the same way, such as making them all too low or too high by the same amount. The size of errors we can quantify by the absolute error or the relative error. The absolute error is the measured value minus the true value. That makes sense. And the relative error is that absolute error divided by the true value. So it's a percent. In example 3, find the absolute and relative error. And it says a projected budget surplus of $17 billion turns out to be $25 billion at the end of the fiscal year. So the absolute error would be $25 billion minus $17 billion. That's $8 billion. And the relative error would be that $8 billion divided by the true, so 17 billion, or the original. 0.471, and we're changing that to a percent, so 47.1%. Accuracy describes how closely a measurement approximates a true value. An accurate measurement has a small relative error. Precision describes the amount of detail in a measurement. So two things, again, that sound the same that aren't. Combining measured numbers, the rounding rule for addition and subtraction, you round the answer to the same precision as the least precise number in the problem. For multiplication and division, you round the answer to the same number of significant digits as the measurement with the fewest significant digits. So addition and subtraction, you look at precision, and multiplication and division, you look at significant digits. To avoid errors, round only after completing all the steps, not during the intermediate. So if you're using your calculator to go through, and of course it's rounding to a certain extent, but you want to use all the decimals it gives you until you get to the very end. So example 4 says, a book written in 1985 states that the oldest Mayan ruins are 2,000 years old. How old are they now? Now, a book written in 1985 is roughly 30 years old, a little bit more than that. But so we might be tempted to just add 30 years to 2,000 and get 2,030 years. So that's the age of the ruins now. However, 2,000 years is the less precise of the two numbers. It's precise only to the nearest 1,000 years. So if you look at this, if we write this out, 2,000 years, which is precise to the nearest 1,000, plus 30 years, which is precise to the nearest 10. Yes, that gives you 230 years, but we must round to the most precise, or the least precise. So must round to the nearest 1,000. So the fact is, we would still say that the Mayan ruins are still only 2,000 years old. Here, the government in a town of 82,000 people plans to spend $41.5 million this year. Assuming all this money must come from taxes, what average amount must the city collect from each resident? Okay, so you would take $41,500,000 and divide that by the number of people, 82,000, to get your answer, right? But keep in mind that this dollar number is only 3 significant digits, and this one is only 2 significant digits. Okay, so let's divide, and we get $506.10. But we need to round to the least significant digits. So to 2 significant digits. So that would only be $510 per person. Because we rounded up to this spot. Okay.